Welcome to a lesson on A mod B when A is negative and B is positive. We know from the previous lesson, the modulo or mod operation returns a remainder when dividing based upon the division algorithm, where the division algorithm states given any two integers A and B, we can always find an integer Q such that A is equal to Q times B plus R, where R the remainder is an integer that is greater than or equal to 0 and less than the absolute value of B. This indicates R is non-negative. In the last lesson, we learned that 7 mod 3 is equal to 1 because 1 is a remainder when 7 is divided by 3. 7 divided by 3 is equal to 2 with the remainder of 1, or using the equation from the division algorithm, we can express 7 as 7 equals 2 times 3 plus 1, where again 1 is the remainder. But the question now is, what happens when A is negative and B is positive? Let's look at several quotients. Let's first consider negative 10 divided by 5. There's no issue here because A, or negative 10, is a multiple of B, or 5. Negative 10 divided by 5 is equal to negative 2 with the remainder of 0. Or using the division algorithm, we can express negative 10 as negative 2 times 5 plus 0. This indicates negative 10 mod 5 is equal to 0. But what about negative 11 divided by 5? Should we express negative 11 divided by 5 as negative 2 with the remainder negative 1? Which means we can express negative 11 as negative 2 times 5 plus negative 1, or should we express negative 11 divided by 5 as negative 3 with the remainder of 4, meaning we can express negative 11 as negative 3 times 5 plus 4. And notice how we have a similar situation for negative 12 divided by 5, negative 13 divided by 5, and negative 14 divided by 5. Should we use these negative remainders, or should we use the positive remainders? And this goes back to the division algorithm, where R must be greater than or equal to 0 and less than the absolute value of B, or in our case, the remainder R must be greater than or equal to 0 and less than 5, which means we need to use remainders here on the right side when evaluating A mod B when A is negative and B is positive. And therefore, negative 10 mod 5 is equal to 0, negative 11 mod 5 is equal to 4, not negative 1, negative 12 mod 5 is equal to 3, not negative 2. Negative 13 mod 5 is equal to 2, not negative 3. And negative 14 mod 5 is equal to 1, not negative 4. The good news is when we have a negative number mod a positive number, we can use the following formula for the mod operation. Negative A mod B is equal to B minus A mod B. As an example, to evaluate negative 12 mod 5, using the formula we have 5 minus 12 mod 5. 12 mod 5 is equal to 2, since 2 is a remainder, when 12 is divided by 5, giving us 5 minus 2, which is 3. With all that said, I do want to mention some programming languages will return a negative value for A mod B. This is because instead of requiring R to be greater than or equal to 0 and less than the absolute value of B, the requirement is the absolute value of R must be less than the absolute value of B. But we're going to stick to the requirement for R given by the division algorithm. Let's look at some more examples. First, we have negative 25 mod 7. Let's first apply the formula. Negative 25 mod 7 is equal to 7 minus 25 mod 7. And now we determine 25 mod 7 by determining the remainder when 25 is divided by 7. We did this in the last lesson, but we'll go and show it again. There are 3 7s in 25. 3 times 7 is 21. The difference is 4, giving us a remainder of 4. This indicates 25 mod 7 is equal to 4, giving us 7 minus 4, which is equal to 3. To check this, we'll make sure we can form an equation given by the division algorithm where R is equal to 3. And we can. Negative 25 is equal to negative 4 times 7 plus 3, verifying our work is correct. Notice the remainder R is greater than or equal to 0 and less than 7. Next, we have negative 47 mod 12. Using the formula, this is equal to 12 minus 47 mod 12. Next, we determine 47 mod 12, which is equal to the remainder when 47 is divided by 12. There are 3 12s in 47. 3 times 12 is 36. Subtracting, we have a remainder of 11. Going back to our work, this gives us 12 minus 11, which is equal to positive 1. 1 is the remainder greater than or equal to 0 and less than 12 when negative 47 is divided by 12. Checking our work, Negative 47 can be expressed as negative 4 times 12 plus 1, verifying our work is correct. Next, we have negative 123 mod 10, which equals 10 minus 123 mod 10. 123 mod 10 is equal to the remainder when 123 is divided by 10, which is 3, giving us 10 minus 3, which is 7. Again, notice 7 is greater than or equal to 0 and less than 10. Let's just check to make sure we can express negative 123 in the form of negative 123 equals q times b plus r, which we can. Negative 123 is equal to negative 13 times 10 plus 7, verifying our work is correct. And then for the last example, we have negative 483 mod 15, which is equal to 15 minus 483 mod 15. To determine 483 mod 15, we divide 483 by 15 and determine the remainder. There are 3 15s in 48. 3 times 15 is 45. We subtract the difference is 3. Bring down the last digit. There are 2 15s in 33. 2 times 15 is 30. We subtract. The remainder is 3. 483 mod 15 is equal to 3, giving us 15 minus 3, which is 12. Again, 12 is greater than or equal to 0 and less than 15. Let's finish by making sure we can express negative 483 in the form of the equation given by the division algorithm. Negative 483 is equal to negative 33 times 15 plus 12, verifying 12 is correct. I hope you found this helpful.